Okay, so this is the continuation of 17.2. Again, this is Mrs. Vanderwalle with the Blank Wall series. So hopefully you had a chance to actually do problem number 3 on your own before coming back. And so kind of let's see what's happening here. Well, the first thing that the directions say is to decide which element is oxidized or reduced using the table of reduction potentials. Remember, and this is key, it really is, the more positive reduction potential gets to be reduced. So let's kind of look up these real quick. Sorry about that, that was my chair. So I'm going to check these two out. So I have zinc 2 plus 2 electrons making zinc, and I found that is equal to negative 0.76 volts. Then I found copper 2 plus 2 electrons making copper, and that electron potential is 0.34 volts. So how do I know which one is going to be oxidized and which one's going to reduce? Let's find out. Up here it says the more positive reduction potential gets to be reduced. So which one is more positive? It is the copper. So that is my reduction, and therefore this is going to be oxidized. Well, that means I'm going to have to rewrite this. Okay, so my oxidation I'm going to have is zinc going to zinc 2 plus 2 electrons, and that E for the anode, now that I know this is the anode and this is the cathode, I love my smartboard. And what do I have to do with the sign? I have to put a negative 0.76 volts. Now what does that do? It's a positive. All right, so you have to change the sign when you make it your anode here, your oxidation reaction, and so it becomes a positive 0.76. So okay, now what? We have to reverse the equation, which I did. Balance the two half reactions. If you remember back in chapter 4, and we talked about that, that is where you have to make sure that your number of electrons that are being gained is equal to the number of electrons being lost. And fortunately for us, in this case, they are the same. So we don't have to worry about that. We don't have to go to that next step. It already is balanced. All right, and now what we have to do is add the two half reactions together and then add the voltages together. So let's do that. So here is my copper 2 plus. Now what happens to these electrons? They cancel out, so I don't need to write that. So plus zinc goes to copper plus zinc 2 plus. And what does the voltage equal? Well, E naught for cell, because again, these are at standard conditions, is 1.10 volts. Okay? And there you have it. Hopefully you did something like that too. All right, let's go on to problem number 4. Now this is a tad different. Consider a galvanic cell based on the reaction of the aluminum magnesium setup. So given the balanced cell reaction, and calculate the E naught for the whole cell. All right, so let's find out what's going on here. I need to look up the half reactions for the aluminum and for the magnesium. So I'll go ahead and let's write this down. So here's magnesium. Going from magnesium to magnesium 2 plus. Is that oxidation or is that reduction? Well, where do I need to put my electrons? Which side needs to be more negative? I think it's this side. So is this oxidation or is it reduction? Well, my electrons are being lost. They are my products. Magnesium solid is giving them up. So this is my oxidation. Okay, so then the aluminum becoming, or ion becoming aluminum metal, well, where do I need to put the electrons here? Well, I think the one that's more positive needs to have the electrons, so I need to put the 3 electrons here. So is the aluminum ion gaining electrons or is the aluminum ion losing electrons? And you'll see that it's gaining, so that's my reduction. So I'm going to look up on my chart now and see if this makes sense. when I look up the aluminum as a reduction potential, so E for the cathode is equal to negative 1.66 volts. Well, how about E for the anode? Okay, well, what happened here? You have to do what when you make an oxidation? You have to reverse the sign. And what happens there? So when I reverse the sign, I get a positive value here. I love my smartboard. And notice what happens now. I'm all set that I have flipped them, and I'm going to get a positive E cell, and that needs to happen. So in order for this to be spontaneous, hopefully that rings a bell, because in this last chapter 16, we talked about what it takes for a reaction to be spontaneous, and that was when your delta G value was negative. And in order for a galvanic cell to be spontaneous, you're going to find out, as a little helpful hint, that your E cell needs to always be positive. So there is a relationship, and we're going to discover that in future sections. All right, but I'm not done yet. I have to balance the reaction. So do you remember what we said last time of balancing the reaction? That the number of electrons that you lose has to equal the number of electrons that you gained. Is that the case here? No, it's not. So hopefully remember what to do here. You need to multiply this by 3, and you need to multiply this by 2. And so when we put this all together, we're going to have 3 magnesiums. We're going to have 2 aluminum ions. Notice that my electrons are now canceled. There's 6 electrons when you multiply, whoops, when you multiply this by 2, and when you multiply this by 3. So the number of electrons indeed cancels out. So we have 3 magnesiums and 2 aluminum ions. No electrons are going to show up because they canceled out. And so now I need 3 magnesium, 2 plus, and 2 aluminums. My E naught, my E standard for the cell, is when I add those 2 numbers together, and I get 0.71 volts. So note a couple things here. First of all, I did not multiply these 2 numbers. I did not multiply that by 3, and I did not multiply that number by 2. So even though I had to multiply the 3 here and the 2 here, you do not do that when you solve for the electron or the electrical potential here. You do not change the volt numbers. It's whatever's on the chart, that's the number you're going to use. Do not multiply. Why am I repeating myself? Because students will want to do that. Please don't. All right, what else do you notice? Is this balanced? I have 3 magnesiums here. I have 3 magnesiums here. I have 2 aluminums here. I have 2 aluminums here. Is the charge balanced? I have an overall charge here of a +6, and I have an overall charge here of a +6. So I do believe everything is balanced out. Again, notice I do have a positive reading here, which you must have a positive reading. All right, so we're done with problem number 4. Let's go on to the next page. All right, problem number 5. This is a little bit more complicated. So go ahead and balance this. You need to go back and look at those potentials that I gave you on that sheet and follow the same procedure that we've done on the last 2 problems. See how you do, balance the equation, and calculate the E naught for the cell. Pause this while you work it out and see how you do. Okie dokes, welcome back. Let's see how you did. Well, the first thing I did is I looked at the permanganate. So MnO4 negative. And let me see, oh, here is where the manganese ion here. And so I'll put it there. And I have to balance my oxygens next. So I need to put 4 waters here. Ruh-roh, I need to balance my hydrogens next. I have 8 hydrogens. So you remember how we did that? Put your 8H plus there. So now my manganese ions or my manganeses are balanced, my oxygens, my hydrogens are balanced, my charges are not. And this is what determines where the electrons go. So I have an overall charge here of +7. I have an overall charge here of +2. So I need to put some negatives in on the reactant side. Looks like I need 5 electrons. So I'm going to put 5 electrons right here. Let me erase this. So that's the first one. And then I went ahead and I did the chlorate ion next, becoming perchlorate. And my oxygens are not balanced, so I need to put in a water, just one water, so the oxygens work out. And I have 2 H pluses here. So now everything is balanced except for the charge. I have a -1 charge here. I have a +1 charge here. I need some electrons on my product side. Looks like I need a total of 2 electrons to make it work out. So now I have a -1 charge on both sides. So let's check this out. If I were to look at my oxidation numbers, all right, the oxidation number here is actually +7. How the heck did I do that? Well, the oxygen, each oxidation number of oxygen is -2. So what number? -8 equals -1, the charge. So manganese is +7. And it goes to +2 here. So did it indeed get reduced? Yes. Why do I need to worry about that? Because I need to know which is at my cathode and which is at my anode. So it looks like the permanganate is my cathode. It got reduced. So its value was 1.51 volts. That means the chlorate going to perchlorate must have been oxidized. It makes sense because here I lose 2 electrons. And also let's review the oxidation number for the chlorate ion. So what number -6 equals -1? I think it's a +5. And same thing over here. What number -8 equals -1? This is +7. So that makes sense. My oxidation number went up. It was oxidized. I lost 2 electrons. Good. I know that this is my anode. And so what does that mean? I need to look it up on that chart that I gave you, and notice what I have to do. I have to reverse the charge. And now when I'm ready to do this, hang on, I need to scroll up. I will need to balance out the ions here, and I will need to add those 2 together. So let's check it out. You end up with 2 MnO4, -+6H plus 5 ClO3 goes to 2 Mn +2 +3 H2O +5 ClO4 minus. The E for the cell ends up being 0.32 volts. How did I do that? I had to multiply this by 5, and I had to multiply this by 2. For the electrons to balance out. And there you go. So the next little thing we have to worry about is what's called a line notation. And this is pretty easily done. This is where you take your anode to your cathode. It's in alphabetical order. And the double lines indicates where your salt bridge goes. And then on each side, you need to give me the phase boundary. So start with your electrode to solution, solution to electrode. So it says write the line notation for problem 3 above. That was our zinc and our copper problem. So which one was the anode and which is the cathode? That's what we need to go back and look at. So over here, our anode is our zinc. Our cathode is the copper. So to figure out the problem then is, whoops. Nope, sorry. Sorry about that, guys. All right, so our anode was the zinc. So anode to cathode, and now this is in alphabetical order. So it is your zinc solid in a phase boundary with a zinc 2+ at a 1 molar. And then I have the copper 2+ at the 1 molar. That's a 1 point molar, sorry guys, to the copper. And there you go. All right, go ahead and we'll stop this now and go back, and now let's do part 3 of section 7.